Welcome to this introductory offering of our course, The Mathematics of Waves. This is the third lecture of week 2. Now, in the last lecture, we were talking about this concept of normal modes, but we were talking in terms of a discrete circuit, like this ladder circuit, where you had these LC sections, each section being like an oscillator, and when you put them all in series, you get a wave system. And we're making the point, this very important conceptual point, that a wave system like this was behaved as if you had lots of independent oscillators. So if there were, say, 10 sections, then you had the 10 independent oscillators. And our discussion was in terms of this equation that we wrote down, where you had, so if you had 10 sections, you had these 10 currents and 10 voltages. Right? And so this was a 10 by 10 matrix, that's another 10 by 10 matrix, and so on. And this was the basis for our discussion of normal modes. Now, what we want to do in this lecture is to go to the continuous limit of this, where this length of a section goes to 0, so becomes smaller and smaller, but the inductance per unit length stays fixed, and the capacitance per unit length, they stay fixed. And so as you make A smaller and smaller, the velocity approaches a constant, in the sense the inductance per unit length and the capacitance per unit length are fixed. So you get a certain velocity. But this corresponding omega, that tends to a very large value because A is tending to 0, so the product has to stay constant. So that's what you might call the continuous limit of what we were doing before. And that's relevant to many physical systems. You see, I mean, some physical systems are indeed discrete, have discrete sections like this ladder circuit. True. But there are other physical systems like a coaxial cable, or where you have an inner conductor and an outer conductor, and which can be modeled as little LC sections, but then it's continuous. So you should, as you make A smaller and smaller, this becomes a more accurate representation of the real thing. So that's what we want to do in this lecture. Go from our discrete limit, as we were doing before, to this continuous limit. Now, in the discrete limit, we had this matrix B, and when it acts on a set of voltages, if you have n sections, you got n voltages. What you get is differences like this, V2 minus V1 or V3 minus V2. Why is that? Well, basically B has 1 on the diagonal and a minus 1 on the lower diagonal. Right? So the second row gives you V2 minus V1. And this first row actually wants to give you V1 minus V0, but we don't have a V0. But because of periodic boundary conditions, you get a Vn. That's this minus 1 out here. Okay. Anyway, so in the discrete case, B acting on a column vector gives you something like this. Now, as we let this A to tend to 0, the point is that these differences can be written as A times the derivative of V with respect to x. So here we are making a conceptual step from what we were doing before to where we are going now. Because previously, V was just a function of time. No x was involved. I mean, sure, we had n of them. We had V1, V2, V3 telling us the voltages at different nodes. But each one of them was just a function of time. And so we had an ordinary derivative here, not a partial derivative, because the only independent variable was time. Now we are thinking of a quantity V, which is a function of x and time. So we don't quite have that V1, V2, V3, n of them. What we have is a Vx comma t. And so now you have a partial with respect to x and a partial with respect to time. Okay? Okay. Anyway, and the point is that these differences can be written as a times the partial derivative with respect to x. And the same works for B transpose as well. B transpose also involves these differences, but it's a little different because when you take B transpose, then the -1 is not on the lower diagonal, but rather is on the upper diagonal here for B transpose. And so you tend to get V2 minus V3 and so on. And the result is that in the derivative, we now have a minus a times the derivative, partial derivative. Whereas when B was acting on it, you had plus a times the derivative. So we can take these two results and replace the original matrix B with a times derivative with respect to x. See? And previously we had a column vector I and a column vector V, each with n components. Now we have a function ixt and a function vxt. And this B operator B, this matrix operator B, got replaced with a times d dx. And B transpose got replaced with minus a times d dx. So the result is now both of these terms have a minus sign there. Whereas previously, if you remember, one was minus, the other was plus. Right? But because of the sign difference between B and B, the effect of B and B transpose, we now have the same sign on both. So this then is the continuous version of the discrete thing that we have been talking about in the last lecture. Now, what we had seen before was that for this discrete thing with the periodic boundary condition, you could diagonalize it. You could write these vectors e to the power minus j n k a, which are eigenvectors of B and also of B transpose. So when you use this, you could use this set of vectors to diagonalize the original matrix, and the net result was, instead of that B operator, you had a diagonal operator whose k component was given by this, and here you had the omega k star. So this I'm just recalling from the last lecture. Now, in the continuous case, what happens is we have a similar result. That is, now I and V are functions of x and t, and instead of being e to the power jnka, it's like e to the power minus jkx. And these functions are eigenfunctions of the derivative operator, because you say an exponential function is an eigenfunction of the derivative, because when you take the derivative of an eigenfunction, it's a constant times the eigenfunction. It's the exponent times the eigenfunction. So when you use this, the d dx becomes minus jk, is equivalent to multiplying the function with minus jk. And the same here, this d dx multiplied by minus jk. And so minus omega times minus jk gives you a plus j omega ka. And here also you get a plus j omega ka. So this kind of diagonalizes the original equations. You could call it diagonalizing. And the thing is that they decouple. So each k is now a separate thing looking like this. And the eigenvalues of this are plus minus j omega ka, meaning that these normal modes, these independent oscillators, now have frequencies that are given by omega times ka. Okay? And that is what you get when you use this differential version that we are now talking about. And again, compare with what we had done before when we had the discrete version. Remember, when we were starting with a discrete circuit and we had these column vectors, that's when we found that these normal mode oscillators had omega k given by this function. Now, when you go to the continuous limit, we get omega times Ka. And these are actually equal as you go to the limit of A tending going to 0, because when this is small, sine of x is like x, and that's how you get the continuous limit. So this is the first point I wanted to get across, is how a discrete circuit can be turned into a continuous one, and the relationship between them. In either case, you have normal modes that you can label with k. But here the normal mode frequencies have this relation, which is a little different from what you have here. Here it's a perfectly linear one, whereas here you have something that's linear only for small k. Now, in the next few slides, let me show you another example of a circuit, of a physical system that would be described by one of these equations that we just obtained in the continuous case. So, and that is the vibrations of a guitar string. So, so far we have been talking about an electrical circuit, this transmission line. Now we are talking about a mechanical system. See? But mechanical system where you have this string that's fixed at both ends and can vibrate. As you know, if you pluck it, it will vibrate. And what I claim is that the mechanical equations describing this vibration can be put in much the same form. Okay. So how do you do that? Well, the way you describe this wire, you see there's this x-axis runs along the wire, and at each point you can define a variable y which tells you how much it has moved away from its normal position. Right? So, when you pluck it, you pull it away from where it wants to be. That's it. And the way you can get the equations into the form we had before is if you define voltage and current like this. Remember, this y is a function of x and t. X because every point in your string has a different displacement. And t because it's vibrating, so it's changing with time. And so the partial with respect to time is what you call the voltage. The partial with respect to x is what you call the current. Now, let's now see what the dynamical equations would look like. Okay, now the first one, which is the di dt is dv dx, that's easy because you see, with this definition, what is partial of I with respect to time? Well, I itself is the partial of y with respect to x. So when I take the partial with respect to time, I get this second derivative, with partial with respect to x and t, these two derivatives. Now, when you do del v del x, there also you get the same thing. It is two derivatives of y, one with respect to x and one with respect to time. They come in reverse order. In one case, it was t first and x next. The other case, it's x first and t next. But for normal functions, that doesn't make a difference. So those are equal. And so del I del t is equal to del v del x. That's the first equation. Now the second equation looks something like this. This is what relates del v del t to del I del x. And this requires a little discussion, but I'm just stating the result first. And there's these two parameters that enter here. One is this mass per unit length, mu, and the tension in the string, which is this Ft. And of course, if you have any experience with guitar strings, you know that both of those things actually affect the frequency that you get. Because, if you look at those wires, usually the bass wires, the ones that have a lower pitch, are the thicker ones, the ones that have a bigger mass per unit length. And the other thing is when you tune a guitar, if you want to get the pitch higher, you make it a little tighter, right? So you increase the tension. So you can see that those are parameters that actually determine the behavior of the string. What are the vibrational frequencies? Okay. Now, how do we obtain this equation, the second equation? Well, you can basically write down the Newton's laws for a little element of this string. So you consider this little element here, and the point is this element is not moving in the x direction, it's only moving in the y direction. So in the x direction, they must have the same force acting, and so it doesn't move. Whereas in the y direction, the force is Ft times the slope of the string at that point, Ft dy dx. And so on the left, you have Ft dy dx at x1, that's left end of this element. On the right end, it's Ft del y del x at x2. And if you look at the difference, then that's the net force acting on that little piece. And so Newton's law is that the force is the equal to dp dt, d dt of the momentum part. And that's where you have this mu delta x, that's the mass, see, and times this acceleration d2y dt2, which is, and m times that would be like the dp dt. Okay? Anyway, so that's what Newton's laws would get you. And now you can put it in the form of these voltages and currents that we had talked about. Because you could divide by x2 minus x1, and then on the right hand side, what you have is the slope of the string at x2 minus slope of the string at x1 divided by x2 minus x1. And as these two get closer together, this becomes like the second derivative of y with respect to x. It's basically the derivative of dy dx. And so going back to our definitions, if you remember, we defined voltage as dy dt. So d2y dt2 is like dv dt. And we defined I as del y del x. So what's on the right here is like the derivative of the current with respect to x. So that's how you get this second equation. Now, you can take this set of equations and put it in the form of a matrix, as we always do, because then you can see the pattern and compare it to what we had been doing before. And basically, you'll have a ddx here and a ddx here, but with a factor ft over mu out here. Now, if you remember, our next step usually is to scale the current variable so that it has the same dimensions as the voltage, and try to make the two elements here become equal in magnitude. So the way you do that is you put in a z0 here that multiplies this by z0 and divides it by z0. And then we choose our z0 such that this is exactly the same as that, which we call v0. And that with a little algebra you can show you'll get v0 equals z0 times and both are equal and equal to square root of ft over mu, the tension over this mass per unit length. So that's what determines the velocity of a sound wave corresponding to these vibrations. Right? Compare with what we had before. Remember, for the electrical circuit we had this equation. Now for the mechanical system, this guitar, with this definition, we have an equation looking like this. And you see they have exactly the same form. One little difference is here we had a minus sign, here we ended up with a plus sign. But that's really an unimportant difference because you can get rid of it. So if you wanted a minus sign here, what you could do is take minus I and call that I. So in other words, change your definition of the current. Instead of being dy dx, make it minus dy dx. If you did that, you'd actually have picked up a minus sign here and a minus sign here, and the equation would have been identical. So whether both are minus or both are plus, that's an unimportant difference. What is important though is the relative sign of the two. because in order to get oscillations and waves, the thing is, in these equations, the two will have the same sign. You can get numerical solutions to this equation if you like, in order to simulate how a guitar string vibrates. But what happens is, you see this continuous limit, we have this partial differential equation. That's good if you're trying to get analytical solutions. But when you want to solve it on a computer, you see, you have all methods to do that would turn it into a discrete set of equations, the ones that we started with. Remember, in this lecture, we started with the discrete thing and then went to this continuous limit. But to solve it on a computer, we'd have to kind of go back to the discrete version. So here what I've done is taken this string and broken up into 50 little segments. So n runs from 1 to 50. And then what I'm plotting is the voltage, this voltage variable as a function of time for each of these 50 segments. And the color tells you how big that voltage is. So when you see the yellow, that's a large positive number. When you see the blue, that's a large negative number. And the green is kind of 0. So you pluck the string, so you have in the middle, you have a big voltage, or you have the big displacement here, right there. And then when you let it go, it starts vibrating. So it goes from some positive value to some negative value, again to some positive value, and so on. And if you compare with the electrical system, actually the boundary conditions. Here the boundary condition is that the two ends can't move. You have locked them down. They have a current because dy dx, you notice the slope is not 0 there, but dy dt is 0 because they're always, y is always fixed there, always 0. You see in the simulation, it's all green at the two edges. And this corresponds to, in the electrical sense, putting the voltage to 0, which is what we normally call a short circuit. So this thing with the guitar string plucked, the way you have set it up, would correspond to the electrical system having a short circuit at both ends. And then you are plucking it in the middle, that is setting some voltage in the middle and then letting it oscillate. And letting the voltage, oscillate over time. So those would be kind of equivalent things described by similar equations. But of course, physically very different. One is a mechanical system, one is a electrical system. One other point I'd like to make here is that these equations, you can also put it in a slightly different form, which is usually what wave equations look like in the literature. When you look for wave, if you just Googled wave equations, you usually wouldn't get an equation looking like what we have here. It will look a little different, but you can easily get to that form. The way you do it is, here we wrote this in matrix form, but let's actually write out the equation, meaning, this matrix d dt of z0i is minus v0 d dx of v. So that's this first equation. Similarly, the second equation. And as we noted, these could be both plus or both minus. That's why we have put in this plus minus. Now what I can do is, I can take this second one and take the partial with respect to time. Then you see the left hand side becomes the second derivative of v with respect to time. That's what I have here. The right hand side becomes the derivative of I with respect to x and t. But then I know that the derivative of I with respect to t is actually derivative of v with respect to x. So finally what I have is second derivative of v with respect to x, partial derivative of course. So these two equations, which involved first derivatives, can be combined into a single equation, but which involves second derivatives. And usually wave equations are often written in this form. Right? Although in this course, in general, I've been using the version where you have first derivatives, right? And of course you have multiple components. Here you had a current and a voltage, whereas in this form you could have just voltages or just currents, for example. But I just wanted to show you how our form could be massaged to look like this other form that you may have seen. But the main important point, though, that I was trying to make in this lecture is this passage from the discrete version to the continuous version. Because there are physical systems which are discrete, in which case, of course, the discrete version is what you really want, where you have these column vectors, each one having, say, 50 components if there are 50 sections. And then you have this matrix B that we talked about, and the normal mode oscillators are then given by this expression. Right? This is often called the dispersion relation. But in the continuous case, guys, the dispersion relation is linear in the sense that the oscillators are proportional to k, and the proportionality is this velocity of the wave, that's v0. And instead of having these column vectors, you now have a current which is a function of x and time. Okay? Now, there are many systems which are actually continuous, and in that case, this is the more appropriate version. And but then if you want to solve something numerically, usually although you might start from here, you try to make approximations to put it in this discrete form. And in that case, you have to remember that you should make A really small in order to get a proper representation of the actual continuous system. I'd mentioned the coaxial cable as an example of that. And the guitar string is also an example of that. So you don't quite have discrete things here as it stands. It's really a continuous string, right? Of course, if you went down to atomic levels, then you could say at the atomic level things are discrete, etc. Anyway, but the important point I wanted to get across was this discrete version and the continuous version and the relationship between them. And going forwards then, in this last lecture, what I will be doing is the 3D version of this. So here what we are talking about is waves in one dimension. But next we'll pick up waves in 3 dimensions using electromagnetic waves as a primary example. Thank you.